Hi everyone, I am Rishon Fernandez and I have a terrible cold. Today I am going to give a talk on ideals, utility of ideals and how they save prime factorization. But before that, a small advertisement for my next talk. When you look at these equations, are you like this guy or that guy, or are you Diophantine equations? So these equations look very confusing and weird, and they don't seem solvable with elementary techniques that we have learnt until now, elementary number theory techniques without ideals and algebraic number theory. But these problems, I will teach you how to solve these types of problems in the next class with the help of ideals. So pay attention to what is being done in this class, because that will be in lot of use next class. You cannot do this without what I am going to teach today. Set theory preliminaries. A set is a well defined collection of objects. So when we say well defined collection of objects, it means that either something, some element you call it, is in the set or it's not in the set. For example, in that S is equal to ABC, if you ask me whether D is in the set, it's not. It's clearly not in the set. And if you ask whether C is in the set, yes, it is in the set. It's well defined. Similarly, S is equal to 2k, where k belongs to integers, that is the set of even numbers. You can clearly say whether a number is in the set or not. 2.5 is not in the set because it's not even an integer. 1 is also not in the set because it's not even, but 2, 4, 6, 8 are all in that set. Then A is a subset of B. This symbol is called subset. It means every element in A is contained in B. The operations on sets A and B are A union B. The smallest set containing both A and B is A union B. Okay, you have the set, some set A union B, then all the elements of A and, okay, it contains only the elements of A and B, nothing else. This all is not in this. So only these two parts. It's somewhat like the sum of thing, not exactly like the sum, but it's the smallest set containing both A and B. A intersection B is the largest set contained by both A and B. Okay, you can have smaller sets as well, like it's just the set of all common elements. You can think of it like that. Next slide. Rings and ideals, a short review. Anyways, definitions. Commutative rings. A set R equipped with two operations, addition and multiplication, plus and into x, such that A and B belonging to R, then A plus or minus B and A into B belong to R. That is basically the closure property. The set, what set you take, is closed under addition and multiplication, the two operations that you have defined. Then the second property is the set R contains a 1 and a 0. That is essentially the identity property. It contains an additive identity which is 0. You add anything to 0, you get the same element, and 1, the multiplicative identity. You multiply anything with 1, you get back the same number. Then the distributive law holds A into B plus C is equal to A into B plus A into C, and especially in commutative rings, which is what we are dealing with, multiplication is commutative. So some examples of commutative rings are real numbers, rational numbers, ... Ideals are subsets of a ring R with the property that whenever A and B belong to I and X and Y belong to R, Ax plus By belongs to I. This is quite a mouthful, but this definition is convenient, it's compacted. All this definition is telling us is that 1, the set, the ideal is closed under addition. So A plus B belongs to I whenever A and B belong to I. And one more thing, it's sort of similar to closure under multiplication, but it's rather all multiples of an element. So whenever some x belongs to I, all multiples of that x, that is R of x, belong to I. Okay, so whenever x belongs to I, all multiples of x belong to I. Those are the two properties of ideals, defining properties of ideals, and I is a subset of R. So for example, the ideal 2 from integers signifies all multiples of 2 in the ring integers, even numbers. 4 plus I from z of I, and In general, multiples of an element A form an ideal A called a principal ideal. These are principal ideals essentially have one single generator. Now a generator is something that generates the whole set, See these properties, notice they start with some A and B belong to I. The defining properties of I require some elements to be there in that set, right? Then you can generate the whole set if you think of it in that way. So what these generators tell us is this generator, this A is the generator in this, is what the set will be based on these two properties. Now A, the ideal A, matlab R times A belongs to A, and for all A, that's all multiples, and then the sum of each individual of each to any two elements. So those ideals which have only one generator, right, one single number inside these two brackets, are called principal ideals. So these 2 and 4 plus I are principal ideals, but 2 comma x, I am giving an example of a non-principal ideal. This ideal belongs to the ring z of x, that is all the polynomials with integer coefficients. So p of x equals a naught plus dot 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 plus a of n x power n, where a naught, a1 dot 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 belong to integers. So this ideal over here 2 comma x is a non-principal ideal. All elements in this set are of the form 2 p of x plus x times q of x for any p of x. For any p of x comma q of x belonging to z of x. It's just the definition itself, but here every element is a polynomial in z of x, so it's defined that way, 2 comma x. This what is the thing with non-principal ideals is that they can't be written in a single element. Sometimes you can have multiple, you can represent the same ideal with 2 generators, with 1 generator also, that is also possible, but these cannot be represented with one generator. So that is, you can think of it as somewhat a degree of an ideal. Okay, next, the arithmetic of ideals. The product ij of two ideals is the smallest ideal which contains all the products of elements of I with all elements of j. Essentially every ij is the smallest ideal such that every small I small j, this belongs to I, this belongs to j, all of this, every combination belongs to ij. But that doesn't mean we can define ij as in the set, when you're writing the whole set as well, set itself, ij where I belongs to I and j belongs to j. This I'll explain in the next slide, but now let's move on to I plus j. I plus j is the sum of two ideals. It's just I plus j. Okay, we'll move on to the next slide. These are the set theory definitions. Okay, now notice the I plus j is simple, it's fine, you can figure it out on your own. Just think of, look at I, the product of two ideals I. It is the smallest ideal which contains all products of elements of I with elements of j. But why the summation? Right, this looks really weird. See, there's a reason. Suppose you have, okay, let's say these two ideals I and j, right? You define ij as I comma j, I times j for all I belong to I, j belong to j, right? All products, basically all possible products, but you don't include that something. What that is telling is finite sums. Now see, suppose you have two elements I1 j1 comma I2 j2 belonging to ij in this definition, right? Can you always guarantee that I1 j1 plus I2 j2 belongs to ij? You can't always guarantee that, and that I will show you through a counter example in the next slide. See, consider the ring Z of x. Okay, all the integral polynomials with integer coefficients. Now look at the two ideals. Look at the two ideals, 2 comma x and 3 comma x. Okay, belong to Z of x. See, what is the product of 2 comma x and 3 comma x? 2 comma x times 3 comma x. First we will figure out what each element in this, what the form of each element is. Like we saw ax plus by, where x and y belong to I in the first slide. What the form of each element of 2 comma x and 3 comma x is. So 2 comma x, this ideal in set theory, in set notation, is 2p of x plus x times q of x for all p of x and q of x belong to integral polynomials. Now similarly, can you tell me what each element's form, what is the form of each element in 3 comma x, ideal 3 comma x? 3p of x plus, yeah, every combination of this basically, right? Combination of multiples in some sense. So what we'll do is we'll change this to r of x for convenience, r of x and s of x. Okay, now take two elements belonging to these two sets, right? Okay, wait, first you look at this. Yeah, okay, you multiply them. See, take any two elements. We'll try to figure out what the product is. Okay, so 2 comma x, so any element from 2 comma x is of the form 2p of x plus x q of x, right? And this times 3r of x plus x s of x, right? What we're trying to show, see, what is the goal now? We take two elements, okay, from this, and we multiply and we figure out, we understand, we try to characterize it algebraically. Okay, then you see x belongs to 6x, 6 comma x. Notice that, I'll show you how that is. Yeah, okay, wait, okay, we'll try to characterize it like this first. Multiply it, open it up, 6p of x times r of x. This is 6p of x times r of x plus x into 2p of x s of x. See, we multiplied this out first, 6 into p of x into r of x plus 2p of x into x s of x. So we took the x common outside, plus again x into q of x, 3r of x. So 3 q of x r of x, and then plus 1 constant of x plus 6 p of x and r of x. It's p of x, r of x. Okay? X squared. Oh, yes. Sorry. X squared. Q of x. Yes, see, multiply. This is our definition, right? We're trying to somehow figure out why that summation came. Why that summation came, right? D, Q of x. Yeah. Why that summation came in the definition of multiplication. See, we try. Now, this is how the form of any product looks like. We see that x belongs to 6 comma x. Okay. Yes, fine. That's fine. Sorry, I didn't notice that. Okay. X square q of x times s of x. See, notice this, when you expand it out, you can take it as 6 into some p of x, some polynomial, right? This p of x times r of x can be taken as some v of x, some polynomial v of x, plus x times some polynomial. You take x common over here, okay? So x times some polynomial u of x, right? And this is what if numbers of 6 comma x will be, or they'll be of that form. Okay, we'll go step by step. Excuse me for this. Write it up again. What we're trying to do, we'll go step by step. See, notice 2 comma x times 3 comma x is equal to 6 comma x. We'll prove this by first showing that this LHS is a subset of 6 comma x, and then 6 comma x is a subset of this. Okay. So when we multiply this out, already we saw that this is of the form 6 times u of x, or some polynomial u of x, plus x times v of x. Right. So all elements of this are of this form, and all elements of 6 comma x already they are of the form 6p of x plus x q of x, right, by the initial definition. Did you guys get that part? So since every element of this is of this form, they already belong to this, right? Every element from this LHS, this all belongs to 2 comma x into 3 comma x. But we also know that any element of this form belongs to 6 comma x. So we somewhat showed that this is a subset of this, right? 6 u of x, but 6 u of x plus x v of x already belongs to 6 comma x. So we've showed that every element from this product is already in this right hand side product. So therefore 2 comma x times 3 comma x is a subset of 6 comma x. Okay, did you guys get this part till here? Fine. Now we'll show the other relation. You can work it out on your own side by side, so you'll understand more. Now you take 6 comma x. Everything in this form is of the form, every element in this ideal is of the form 6p of x plus x q of x, right? And you can write this as 2 times 3 p of x plus x q of x, x q of x. Now to somehow we have to argue that this belongs to this product. So anything that belongs to 6 comma x also belongs to this product. This belongs to 2 comma x and it also belongs to 3 comma x. Therefore it belongs to their product. So see, notice that this is 2 times 3p of x plus x times q of x. This is what elements of 2 comma x are of the form. So this belongs to 2 comma x. Similarly, 3 times 2p of x plus x times q of x, that also belongs to 3 comma x. Therefore, since it belongs to both the sets, it belongs to their product also. This belongs to, which implies this 6p of x plus x q of x belongs to 6 comma x, sorry, it belongs to 2 comma x times 3 comma x. So now we showed that every element that belongs to 6 comma x belongs to 2 comma x times 3 comma x. So 6 comma x, the ideal, is a subset of 2 comma x times 3 comma x. Before we showed the other relation, 6 comma x is a superset of this. So when a is greater than or equal to b and b is greater than or equal to a, what can you conclude? A is equal to b. Similarly, 6 comma x is equal to 2 comma x times 3 comma x. Sorry, it wasn't that clear, but just take it for now. We'll follow the next steps. Anyways, 2 comma x times 3 comma x is equal to 6 comma x. Now notice x belongs to 6 comma x. Why? The ideal 6 comma x. Can it be written in the form 6p of x plus x q of x with integer polynomials p of x and q of x? Yes, right? Just choose p of x as 0, 6 times 0 plus x and choose q of x as 1. So this is equal to x. X belongs to 6 comma x. But can you write, it must be there. If not 0 polynomial, there is a multiplicative identity, additive identity, which gives 6 times 0 is equal to 0. Fine. Anyways, 6 times 0 plus x times 1 is equal to x. This belongs to 6 comma x. But can you write x as 2p of x as some product of, let's say, ij with I belonging to 2 comma x and j belonging to 3 comma x? Can you write it this way? Or try to come up with a contradiction on your own that it can't be written. What we'll start with is let's suppose it can be written in this way. Then what is the form of I and j? X is equal to, I will be of the form, since I belongs to 2 comma x, it will be of the form 2p of x plus x q of x, right? This will be the form of I. And what will be the form of j correspondingly? Yes, x s of x, right? I belongs to 2 comma x, j belongs to 3 comma x. Okay, you multiply everything out, what you will get is same thing, 6 p of x r of x plus x into 3 q of x, x into 3 q of x r of x, q of x r of x plus q of x s of x plus x square into q of x s of x, q of x s of x. See, now notice at this point you're just equating coefficients, right? It's a polynomial, we know how to solve this. The left side is degree 1, the right side has an x squared. So what does that mean? What does that tell you about q of x and s of x? Yes, q of x times s of x must be 0, right? Q of x times, I'll write, instead of q of x and r of x, p of x, I'll just write q, p, r, s, whatever, okay? So q times s is equal to 0. What does this mean? Q is equal to 0 or s is equal to 0, because this is a domain. Yes, this is a domain. Z of x is a domain. Domain means there are no non-zero divisors. The same thing, if q times s is equal to 0, implies q is equal to 0 or s is equal to 0. Now we'll plug in, we'll take cases, right? So first case is q is equal to 0. If q of x is equal to 0, what happens? Just plug in wherever q of x is there, just put 0 and check. So first term remains the same, 6pr plus x into This is through P of x 2ps plus 0. Done. That's it. Now notice this is a multiple of 2, right? You can take 2 outside. 2 into 2 in, sorry, this is 2. 2 into 3pr, yes. 3pr plus x ps, right? But is x a multiple of 2 in z of x? No, right? It can't be written as a multiple of 2. If you take, you'll get some half somewhere. It's because we are considering only integral coefficients, and x is like, it has one coefficient, 1 as its coefficient. It is not a multiple of 2. You can clearly see that. So this is a contradiction. Q cannot be 0 because we are getting such an equation where x is a multiple of 2. Similarly, if you take s is equal to 0, you do some thing, you will get some 3 into something. Again, this is a contradiction, right? You can think of it like this. See, whatever you get inside here is an integral polynomial, not integral, of polynomial integers with integer coefficients. But if you divide this by 3 on this side, what will happen is, right side you have a polynomial with integer coefficients, left side you have 1 by 3, which is not a polynomial equation, integer coefficients. It's a contradiction. So therefore both cases cannot be, which means our initial assumption must have been false, that x can be represented as a product from 2 x and 3 x, which means we need finite sums. Can you go back to the previous slide? That is why, you see, in this case clearly you saw for 2 x times 3 x, what we did is we showed that it is equal to 6 x first without any trouble. That was some trouble, but 2 x times 3 x is equal to 6 x, and then what we showed is that x belongs to 6 x, but x cannot be written in this form. But how did we write x initially? It's just the 3 times x minus 2 times x, right? Look at it, it's 3 times x times minus 2 times x. This is just what we defined over there. It's a finite sum. See, x times 2, we'll do it, okay, no, take it, x times 3, now perhaps you'll see it, minus 2 times x. See, this is just a finite sum, it's that summation aij. We saw that this cannot be written as a direct product of I times j, right? It cannot be written as directly from where I comes from 2 x and j comes from 3 x, but it can be written as a finite sum. There are elements which can be written as finite sums but cannot be written as I times j, which belong to that ideal. This x comes from here, this 3 comes from this ideal. So this is I1 j1, then minus this 2 comes from here, this x comes from here, minus I2 j2. It's of this form, summation a I times j. That's why we have that definition. To summarize, there are elements in the ideal which cannot be written as I times j, in the ideal product which cannot be written as small I times small j, for I belong to I and j belong to j. Work it out, okay? So let's move on to divisibility theory for ideals. Any questions until now? Let's move on to divisibility theory for ideals. An ideal I divides j if j is a subset of I. Okay, these are equivalent definitions. Ideal I divides j if j is a subset of I. For example, the ideal 4 is a subset of 2, implies 2 divides 4. 9 is a subset of 3, 3 divides 9. If A divides B, that is B is equal to A is some element. Okay, this is not an ideal. This is to give you intuition for why this random definition of sets comes in. Okay, it seems random, it's not. It feels random. Okay, but A divides B is, this just means B is equal to A times x, right? Ax. And when you take the ideals on both sides, rather not ideals on both sides, you have, see, B is a subset of A. It feels somewhat intuitive, right? That you take the ideal A and you multiply some elements, some X, and you get B, but there are still elements, other elements in A that you did not multiply in some sense, or rather that did not come in this multiplied ideal, that were part of A. That's why B is a subset of A. I hope that gave some intuition. You'll get used to it over time. You'll understand why that definition is like that. Let's get to primes. Whenever there is divisibility theory, there's always a prime number floating around. So we'll define prime. An ideal P is prime if P divides AB implies that P divides A or P divides B. For example, 2 divides AB, some AB, then 2 must divide either A or either B, right? We are talking about normal integers here, because 2 can't be split into 2 more smaller parts. Like if I say 8 divides AB, then you could have that 4 divides A and 2 divides B, because it can be split into 2 smaller parts. But here 2 divides AB implies 2 divides A or B, because it cannot split into, it's irreducible in some sense. So P divides AB implies P divides A or P divides B. That is the definition for prime ideal. And equivalently using the set theory, the subset definition, I have written down there. Okay, next slide. Now we get to some interesting exercise. The GCD and LCM of two ideals. The GCD of two ideals, I and J, is defined as the ideal G, where G divides I and G divides J. Okay, so it's a factor, common factor, and if there exists a G dash such that G dash divides I and J, then G dash divides G, meaning G is the largest common factor. If there is any other common factor smaller than G or any other common factor at all, it must divide G. That is, it is smaller, less than or equal to in some sense, and G is not equal to R, because you could always have the whole set 1 is R. Can you see that? The ring R, if you take the whole ring, the ideal generated by 1 is the whole ring, because you have every element of 1 is of the form 1 times R, for R belong to R, the whole ring, small r belong to big R, and this is just identity. So the whole set R is only the same ideal I. So G is not equal to R. It's the same as saying you have GCD of 2 and 8. GCD of 2 and 8 is not 1, or sorry, 3 and 2. 2 and 8. 2 and 8 is not 1. Okay, it's not 1. Similarly, the LCM of I and J is ideal L, such that if I divides L and J divides L, so I divides L and J divides L, if I and J divide L dash, then L divides L dash, because it's the least common least common multiple. Any other multiple is there, L definitely divides that, and L is not equal to the 0 ideal. Similar case. So here is a nice exercise. Using these definitions, prove that I plus J is the GCD of I comma J. We are talking about GCDs of ideals. I and J are those two ideals. Use the definitions given here, these 3 definitions, and we will try to prove that I plus J is the GCD of I and J. Can we move to the next slide? So we'll go with the proof. Look at these steps, okay? I want you all to try this out on your own, and whenever you have any questions, ask me. I'll explain the steps. I'll give you a couple minutes to try it out. A goal usually with these questions, right, is showing first that I plus J divides, let's take this ideal as G, okay? We'll take it as G. This is equal to GCD of I comma J. We'll abbreviate it to G. So one of the techniques of solving this is you show that I plus j divides g, then g divides I plus j, which would imply I plus j is equal to g. This is what we are going to do here. What is this telling us? This is telling us that g is a subset of I plus j. Here I plus j is a subset of g. Then when these two facts are there together, you can conclude g is equal to I plus j. That is what we are trying to prove here. So we will try to prove I plus j divides g first. Okay. So I plus j divides I and j, right? Why? Why does I plus j divide I and j? Because I is a subset of I plus j, right? Can you see why? You pick the 0. 0 is always contained in every ideal, right? You have r times 0 is equal to 0. Sorry, 0 times I. 0 times I belongs to I for any element. So you pick r as 0, you will get 0 belongs to I, right? So 0 is there in every ideal. So you pick 0 from I plus, you pick 0 from j, and you add every element of I to it. I is contained in I plus. But what about if you pick some other element from j, right? Then there are more elements that are not in I plus. So clearly I is a subset of I plus j. Similarly, with similar logic, j is subset of I plus j. What was the definition of divisibility that told? What did the definition of divisibility tell you about this? Subsets. Two ideals are subset of each other. A divides B, B is a subset of A. So B is a subset of A, I plus j divides I plus j divides I comma j. Did you get this part? Fine. From here, you see, by the GCD definition itself, if there exists g dash that divides I and j, then g dash divides g. So I plus j divides I and j. Therefore, I plus j divides the greatest common divisor, g. So clear. So the argument is I is a subset of I plus j is a subset of I plus j. So I plus j is a common factor of I and j because it divides both of them, which means it must divide the greatest common divisor, g. So here we have concluded our first part, I plus j divides ij. This is 1. We'll put 1 here. Now 2. So that g divides I plus j. How might we show that g divides I plus j? Look at the definition. What does the first point tell you? G divides I and g divides j, right? G divides I and g divides j. But wait, g is an ideal, right? So for every I belongs to I implies I belongs to g, right? Because g is a superset of I. I is a subset, I comma j are subsets of g by definition. So every element in I and j is there in g. Now you take small I belonging to I, that means small I belongs to g as well, right? For any element of I. Similarly, j belongs to j implies j belongs to g. Now g is an ideal. What do you know about ideals? Closed under addition. So for any element of I and j which belongs to big I and big J, I plus j also belongs to g. I plus j also belongs to g. And what is the set I plus j? It's nothing but the ideal of I plus j, right? Ideal defined. This is how this whole set is defined. I plus j. This is equal to I plus j, right? We showed that g contains all numbers of the form I plus j. Essentially, g is a superset of I plus j. We showed that I plus j is contained, all elements of I plus j that are of the form, see, small I plus small j, right? All elements are contained in G, and by the divisibility definition, G divides I plus j. Is the second argument clear? You start with G divides I plus j. This is what we want to prove. We know that G divides I and G divides j, greatest common divisor. That is a given. This means that I and j are subsets of G. This means that I plus j is also a subset of G, because you can pick any I and any j and you add them, it will always be part of G, and that is what all elements of I plus j are, which means G divides I plus j. So from these two facts you conclude that G is equal to I plus j. Done? Now here is a nice homework. Previous slide. Yeah. See, homework is prove that I intersection j. Intersection means all common elements of I and j. Prove that I intersection j is the LCM of I and j. Very similar proof. Try to use the definition of that LCM only, how we used here, right? The hint is prove that I intersection j divides I and j, and then I intersection j divides LCM of I and j, and then show that LCM of I and j divides I intersection j. Then you will get they are equal. Here's some confirmation rather than motivation, some confirmation that all this what we are doing is correct. See, Abhi did Bezout's lemma last time, right? We will try to use that here to confirm what we have done until now. What we have done until now was rather abstract. It was very neat proofs, but it was abstract. What we will do here is we will take a concrete example, integers, and we will show that ideal M plus ideal N is the GCD. See, this is just to get a feel for things, this is not the real actual proof. But notice any element of this number, this what is called this ideal, this addition ideal is of the form mx plus ny, right? But m is a multiple of d, n is also a multiple of d. This whole thing is a multiple of d. Therefore, this is a subset of d. This whole thing belongs to d. Any element that belongs to m plus n belongs to the ideal d. Therefore, m plus n is a subset of d. M plus n is a subset of d. Now, to get a feel for things, just to see that it works, I will show you how to prove. We are somewhat assuming to prove what we have to prove. We are somewhat assuming in the next step. But what we will do is, now we want to show that every element in D is contained in m plus n. See, by Bezout's lemma, you have GCD of a and b for any two integers a and b can always be written as ax plus by. So, isn't D also ax plus by? And every element in this principal ideal is of the form D times, say, a, D times a, okay, D times a. What is D now? It's just, oh sorry, not a, take c, D times c for some number c, some integer c. Any element, any number in this ideal is of the form D times c, it's a multiple of D. And this is again just a c x plus, sorry, a times cx plus b times cy. And isn't this of the form, no wait, oh, sorry, not ax plus by, rather am plus bn, sorry, again the GCD of m and n can be written as am plus bn for two integers a and b. Then what we will do is every element in D is of the form D times C, and you plug in am plus bn in place of D, you will get a times, ac times m plus bc times n. Isn't this just a multiple of m plus n? That's all it is. So we showed now that anything that belongs to D is also contained in M plus N. So D is a subset of M plus N. Therefore they are equal. Okay, that's all it is. It's like this. See, you look at 12 plus 8. What is this ideal? What is this ideal? 4. It's the ideal 4 because 4 is the GCD of 12 and 8. Everything is contained in 4. Okay, this was just to get a feel. But what we would actually do is use the previous test. I'll just outline the argument since it's almost time. Take it down and complete it on your own. Okay. So what we'll do is using the previous definition, what we saw previously, that I plus j is equal to the GCD of I and j. We will try to show these 3 things, and then once we show these three things, automatically we will get Bezout's lemma, as Abhi did it last time. Okay. See, we start with notice one important thing. Here we are taking GCD of 2 ideals, not elements. So if I was to write M plus N is equal to GCD of M comma N. This is what we proved. Okay, this is what we proved in the previous slide. But we want to show that this is equal to the normal definition of GCD, one principal ideal called D, where D is equal to M comma N. D is equal to GCD of M comma N. This is M comma N, GCD of the ideals M and N, and this is GCD of M comma N, normal integers. So first we will argue that GCD of M and N should be generated by one number itself, right? It should be a principal ideal. Why? Because Z is a principal ideal domain. Z integers only has principal ideals, right? That's what we showed. That's what we are trying to show over here. Any M plus N is equal to D. Yes, okay, Z is a principal ideal domain. Didn't Abhi mention that last time? Okay, principal ideal domain, essentially everything has one generator. Everything is generated, there is no, like we saw in polynomials, we saw 2 comma x is a non-principal ideal. But everything in Z can be shown with one element. Any ideal, you add anything, you multiply anything, it can all be shown by one element, some A. Okay. So these principal ideals, first of all we argue that is generated by one single integer D, because it's a principal ideal domain. Now what we want to argue is D is the GCD of M and N. That we will show by D. See, this we will show that the ideal D divides ideal M, ideal D divides ideal N, because see M plus yes, ideal D divides ideal M, ideal D divides ideal N. Why? Because this is the GCD of the 2 ideals M and N. GCD divides the ideals themselves. D divides M, D divides N. It's the greatest common divisor. That is the largest set. D divides M, D divides N. Yes, and because it's a principal ideal, it's similar to working with just integers. Principal ideal domain. Every element, every mx can be represented in the form. This is just, check the first sentence, okay. M is a subset of D, right? And that means any mx for x, some integer x, any multiple of m can be written in the form dy, because it is a part of D as well. Anything that's a part of M is a part of D as well. Now you choose x to be 1 because it's any integer, right? That's identity. So m is equal to d times y, therefore d divides m. Similarly d divides n, right? Similarly n is equal to some dz, so d divides m, d divides n, and it's the greatest common divisor. So if you have any idea, any other this thing, you have any smaller divisor, let's say you have some c, some ideal, some number c which divides m, right, and c divides n, you can take the whole ideal itself, right? C divides ideal m and c divides ideal n. Why can you do this? Because m is equal, the first statement is just telling us m is equal to cx, n is equal to cy. These statements are telling us. When you take ideal, again this is the same as doing what we did in the previous slides, just writing it as c divides c is a sub, m is a subset of c, m, the ideal m is a subset of c, and the ideal n is a subset of c, right? Because when you multiply everything out, see, everything in m, the ideal m is a multiple of m, which is a multiple of c times x, right? But that is already a multiple of c. There are multiples in c, the multiples of c that are not multiples of c and x, which is not multiple of m. Okay, so they are subsets. Okay, anyways, m is a subset of c and n is a subset of c by the ideals, what we saw in the previous two slides, which means m divides c and c divides m and c divides n. But by the GCD definition itself, we saw anytime c divides m and c divides n, it divides the GCD of the two ideals as well. So c divides d. But this again, by applying that same logic, can't we just show that c divides d as well? We can, right? We, again, anything that belongs to d belongs to c. No, anything that, okay, see, you have d is a subset of c, so you pick any element, dx can always be written as cy. You pick one over here, you pick as x, right? So you have dx equals cy, you pick x is equal to 1, you will always be able to find some y such that d is equal to cy. D is a multiple of c, and when d is a multiple of c, for any c, we started with some c divides m and some c divides n, some common factor, right? Then we showed that c must divide d as well by GCD definition, which means d is a subset of c, which means you can show that d belongs to c as well, and so that d can be written in the form cy. C divides d again, so for any c that divides m and n, any common factor, c also divides d, which means d is the greatest common divisor. Did you get that argument? I'll repeat one last time. See, when you have some c divides a, c divides b, and then again this, if whenever c divides a, c divides b implies c divides d, this implies that any common factor divides the greatest common factor, right? That is what a greatest common divisor's definition is. If you have any common divisor, that will always divide that greatest common divisor. Can you go back to the previous slide, Lauren? Previous more. No, next, yeah, here, sorry, stop. See here again, g divides I, g divides g. If there is some g dash, some common factor such that g dash divides I and j, then g dash divides g. That is what we used here, but that is this we used in elementary number theory sense. So anyways, when c divides m, c divides n, we did those manipulations and we came to the conclusion that c divides d, which implies d is the greatest common divisor. Go to the next slide. Next, this is what we wanted to prove. The others I'll give you as homework. Once you prove LCM, right, once you prove that m intersection n, the ideal m intersection n, in the previous slide, sorry, I intersection j is the LCM of I and j. Once you prove that from the previous slide, for general ideals, you will be able to prove that L is equal to LCM of m and n, then m intersection n is equal to L. You have to argue a similar thing. You have to first show that it is the LCM of two ideals, then you have to show that it is generated by a single element, and then you have to show that L is equal to LCM of m and n. Can you go to the next slide? Yes, to sum up everything we have learnt, these are the correspondences. You have in elementary number theory A times B, multiplication. In ideals you have ideal A times ideal B, normal ideal multiplication. When you have A divides B in elementary number theory, you have B is a subset of A, ideal B is a subset of ideal A. And for GCD in elementary number theory, the corresponding thing is the sum of ideals, A plus B, and for LCM of A and B, you have A intersection B. And one last thing, you have units. Did Abhi explain units last time? Units are just one number that divides everything in the entire set. Like you have 1 divides everything in integers, -1 divides everything in integers. So those are what units are. So in elementary number theory, R belongs to R cross, means R is a unit which divides everything in the ring R. That corresponds to, in ideals, the ideal R is equal to the whole ring R. So ideal, let's take it rather as X, right? Let's say X is a unit, then the ideal X is equal to R, for the same reason that time I explained, right? 1 is equal to R, any multiple of 1, so the whole ring R comes in the ideal. Yeah, forward to the last slide. And any doubts you have, you can come to me. I'll be in 10th HB, and you can come and clarify this LCM exercise. Regarding the LCM exercise and any other questions you have about ideals, I can help you out. Yes, thank you.